6.4, enthalpy and delta H, and just work all the worksheet A through F. This is a worksheet that was already given to you. It says enthalpy H and change in enthalpy delta H. The equation that B2H6 plus 3O2. Okay, this is actually a pretty short section, so you might have this one and another one. I don't know, I might do two together, or we'll just check. It'll probably be just one video for this though. Okay, now, so the first lesson I gave you, which might just be like, oh, this information and no math or anything like that. It might have been just so kind of abstract, kind of strange things. The concepts behind thermochemistry. But this is the way that we can really measure changes that occur in chemistry, thermochemistry, is by measuring heat, the heat that's released. And remember, Q is the heat released in an experiment. So if you do an experiment and you set up you'll see what's called a calorimeter. We'll talk about that probably in the next lesson. But Q tells you the amount of heat that's measured off, the heat that it was given off or released or absorbed. Well, when you change Q, so we showed you that equation that energy is Q plus W. So, and I told you to imagine that you have like a cylinder with a movable piston. You can imagine that we live inside a cylinder with a movable piston. Any experiment you do is inside here. And so this is the system. And heat can come out. Like now, if you actually had a cylinder of your own in the lab, a piston, or if you had even a coffee cup, having a coffee cup with hot water in it, you add ice to it, that a thermos or a coffee cup is also like what's called a calorimeter. It kind of keeps the heat constant inside, but of course heat can go in and heat can still go out. If Q is the heat flow into or out of the system. But when you change that into stoichiometry for a particular equation, then it becomes called enthalpy H. So Q changes to H. And that's really what we're going to be using more in most of this chapter. All right, so now I mentioned to you that, let's see here, that I showed you that we're deriving equations. If you read through the textbook, you're going to find all this, like how do they get this equation delta H, all that. We don't even have to worry about that. I'm not going to ask you to derive it. No. It's beyond what we do in the class. It talks about how Q is related to delta H. Don't even worry about it. Don't even worry about that right there. So, this is what we'll look at instead. Here's the main thing. I'm just going to start right off with the equation on example A. It talks about methane. So CH4 gas, methane gas is burned in O2, oxygen, and it says it gives you carbon dioxide and water. Gas and gas. I got to make sure I balance it with a 2O2 and 2H2O. Okay, so there's your equation. This could be going on inside here, in fact. We could have methane in here. We could be burning it inside it. I mean, gasoline is often burned in a piston or in a cylinder. In your engine, that's what happens. The gasoline goes in there, oxygen goes in there, a spark plug ignites it, boom, and then you might get heat. Obviously, heat is involved in around the system, and also changing from a liquid, well, in this case, it's a gas, but changing from a liquid to a gas also causes a change in the volume, which means it does work on that piston. So, anyway, all of that's the best way to think about what thermo is you put something inside this little cylinder that's able to expand or contract. The piston can expand or contract its volume to do work or have work done on it, and then heat can go in or out of the system. That's really what the whole thing of thermo is. And in most cases, we don't even see a change in the volume of the system. So in most changes, it's only the heat we look at. So, all right, here we go. It says on here, in a reaction, 890 kilojoules of heat is released when 1 mole of methane, CH4, is burned at constant pressure. Okay, let me show you what can be done here. Now, for this equation, you could write, it would be correct to write this down. Delta H equals 890 kilojoules. 890 kJ. Now, it should be negative though. It says released, so it should be negative 890 kilojoules. It would also be true to write this down. I'll write it above it. CH4 plus 2O2 gives you CO2 plus 2H2O plus 890 kilojoules. Meaning heat is a product in this reaction. But this is the way that it will normally be written in all this chapter, the whole chapter of thermo. You'll see an equation, delta H, 890 kilojoules. Now, am I going to tell you about the standard yet? No, I'm not going to tell you that. But you might sometimes see a little circle there. You might see a little 298 down there. But everything I'm going to show you will be true. You can use this mathematically. It will always work. Whether it says delta H degrees, delta H 298, doesn't matter. Now, this one just says enthalpy. And I'll explain what that means later on. But for all practical purposes, in a lab, enthalpy is just the heat that's given off. It's actually, it's not just the heat. It's, well, it is the heat, but it's heat given off under special circumstances. As long as you meet these particular standards in your lab, then delta H will be the heat. The enthalpy will be the heat that is released, and it means that the system is allowed to expand or contract at constant pressure. That's what it means. So if an experiment is done in a system that is allowed to expand and contract at constant pressure, then the heat release would be the enthalpy. We call it enthalpy. So you don't even have to really know all that, but that's it technically. All right. So the first question here says, the enthalpy change for the reaction, what is the enthalpy change per mole of oxygen? Well, enthalpy change, number one, is negative 890. So number one, that's the change in enthalpy. Delta H is negative 890 kilojoules. Okay. Number two, what is the enthalpy change per mole of oxygen? Okay, here's what you would do for that one. For number two, the enthalpy per mole of O2. It says negative 890 kilojoules. So delta H, sometimes I'll write O2 down here at the bottom. Delta H per mole of O2 would equal negative 890 kilojoules divided by, look at the equation, how many moles do you have? 2. 2 moles of O2. So 890 divided by 2 is 445. Negative 445 kilojoules per mole of O2. Number 3, or number 2 also, well, I've called that A. We'll call that one, I should put A. B says, what would it be per mole of CH4? Delta H CH4, negative 890 kilojoules per 1 mole of CH4 would be negative 890 kilojoule per mole CH4. This is easy so far. It is easy. It's actually, in this whole lesson today, this little video, this will be pretty easy, and it's just stoichiometry, as you're going to see. Now, what would it be in terms of per gram of CH4? Okay, so now there's a little bit more going on here. What you'll do is negative 890 kilojoules divided by, how many grams would that be? 1 mole of CH4. You'd have to put the molar mass in there. So I wonder, should I just take that number? You can go mole to gram. I'll just put the grams down there. If you had 2 moles, you would have to double it, or 3 moles, you'd have to triple it and all that. Oh, well, yeah, that's true. But I want to, let me think about that first before I do this for a minute. Per mole, let's just say, no, we're going to use the molar mass. So CH4, 12.01 plus 4.04, 16.02 grams of, that's the molar mass of CH4. I added 1 carbon in that. So 890 divided by 16.02 55.6 kilojoule per gram of CH4. Actually, this just reminded me of something very good that you're going to like a lot about the AP questions, and I try to make my questions on the quizzes like the same way. But when it says something like, calculate the enthalpy change, calculate the enthalpy change in kilojoules per gram of CH4, well, that tells you what you're gonna divide in kilojoules per gram of CH4. So look at the problem, and if they gave you the number of kilojoules, like negative 890, and they gave you a number of grams, you would divide those two out, and that would give you the enthalpy change. Now, in this case, it was per 1 mole, so we used the molar mass. The 1 mole of CH4 weighs that. That will be true, stoichiometry. But usually what they do is they have you figure this out. They don't give you that. They usually don't give you this number. Or maybe they'll just say, you'll see why later. I should take it back. They will give you the number. But what they'll do is they'll give you grams of CH4, and you'll divide them out, and it will work out right. But anyway, okay, but kilojoule divided by gram gives you negative 55.6 kilojoules are released of heat for every gram of CH4. Now, why do these numbers matter? All of these are ratios. And just like we did molarity or density or whatever, every 1 mole of oxygen that burns will give off, in this reaction, negative 445 kilojoules of heat. Every mole of CH4 that burns gives off negative 890 kilojoules of heat. And every gram of CH4 that's burned, will give negative 55.6 release. So this helps you with stoichiometry. So let's do the stoichiometry, and you'll be happy about this. This is going to be easy stuff. Okay, number 3, it says, what will be the delta H, enthalpy change, for a process in which 5.8 grams of methane completely undergoes combustion? 5.8 grams of methane. Now, this can also be asked a different way. We could say how much heat will be released when 5.8 grams of methane are completely reacted or burned in this equation. So here's what you do. You say from grams of, now I could take a shortcut, but I'm not going to take a shortcut. I'm going to do it the longer way. We found a moment ago a ratio of gram to kilojoule. I could use that conversion right here if I wanted to. But I'm not going to do that because we don't always find that conversion. If you do, you can use it, but oh well, I won't here. From grams of CH4, I'm going to first go to moles of CH4. And I know that 1 mole of CH4 weighs, I'm going to add together 1 carbon and 4 hydrogens. So the same number I had before, 12.01. So it's 16.05 grams. Now, this will get me from gram to mole. Oh, and by the way, it said, I forgot to write this down. What will be the enthalpy change when 5.8 grams of methane are burned? They want you to find heat. What will be the heat released? How many kilojoules of heat will come out when you burn 5.8 grams of this? Okay, first we go from gram to mole. Now, here is the brand new, the cool thing for thermo. I can now convert from moles of CH4 to kilojoules of heat. How do you go from mole to kilojoule? You know how to go from mole to molecule, 6.022 10 to the 23rd. How do you go from mole to gram? Use a molar mass. Mole to liter of a solution, you use molarity. Remember that? Molarity gives you how many moles for every 1 liter. If you want to go from mole to liter to a gas, use PV and RT. If you want to go from mole to kilojoule, a new conversion, you use delta H. And delta H tells you how many kilojoules per mole. Now, if you have the numbers I wrote down a moment ago, you could actually use those numbers, and they work out. In number 2, we found out what all the ratios were. But you don't have to have the ratios if you have delta H. So what I'll do is this. Negative 890 kilojoule, that goes on the top. That is in perfect ratio with all of these, which is 1 mole of CH4. Okay? Now, if I've been using O2, it would be negative 890 for every 2 moles of O2, or negative 890 for 2 moles of H2O, or negative 890 for 1 mole of CO2. So it perfectly matches the stoichiometry. So, we talked about Q being heat. In an experiment that you do, Q is the heat you measure in or out. Delta H is when you take that Q value and you translate it to match stoichiometry of the reaction. Stoichiometry under some certain thermo conditions, as long as these experimental conditions are met. Okay, so anyway, that works out. So even if I looked up here, same thing. This is in ratio 890 kilojoules for every 2 of these, or 890 with 2 of those. Just remember, if you ever see that kilojoules on the right side is coming out, so it's negative. That's a negative number. Okay, you don't always see the negatives. All right, anyway, let's get the answer to that. So 5.8 times 890 negative divided by 16.05. So we get negative 322. I guess that 890, we'll assume is a dot after it. I didn't write that down. But negative 322 kilojoules. So 5.8, double check it. Yeah, there it is. Okay, that's how much heat will be released when 5.8 are burned. All right. Number 4. I didn't put. Okay, how much heat released when 4 moles of oxygen completely react with methane? Okay, these are pretty simple. I don't even know if you need to watch all these lessons, but these problems here. I'll do one different one at the end here, though. Okay, how much heat will be released when 4 moles of oxygen gas? So we're starting with 4 moles of O2. How much heat? That means I want to know how many kilojoules. Another way to word it will be released when 4 moles completely react with excess methane. That just tells you that O2 would be the limiting reagent in this experiment when it says the word excess. It doesn't change anything, but it's good to keep in mind that sometimes there might be a limiting reagent. Okay, there's not. Well, that is the limiting reagent, they're saying. All right, so from moles of O2, I can go straight to kilojoules of heat. Same equation, negative 890 kilojoules for every 2 moles of O2. So see, if you wanted to, you could put 1 and, what was that, 890 over 2, 445. 1 and, we found that on number 2 before. But there's not really a need much to do that here. Sometimes that shortcut will help you, but to me it's just easier to look at this, and plus when I double check, negative 890 kilojoules. O2, 2, they match. It's easier to double check yourself that way, I think, because what if you mess up the other math? Well, oh well. But sometimes it will be good to use the answer from one problem. It'll save you some time. And they do that on the AP a lot. So you'll see ABC and then all that happens. It looks like negative 1780 kilojoules. 4 times 890 divided by 2. Negative 1780 kilojoules of heat will be released. And then number 5, how much heat is evolved when 20 grams of water are produced in the reaction above? 20 grams of H2O. All right, if we produce 20 grams of water, how much heat also came out during that? Okay, well, I can do the same thing with water, stoichiometry. But, of course, from water grams, I got to get to mole. Moles of water. And you know, because you memorized that 1 mole of water is? Good. I heard that. 18.02. Very good, very good. 18.02 grams. You should know the molar mass of water. Then from moles of H2O, I can now go to kilojoules. Negative 890 kilojoules. So kilojoule, mole to kilojoule. Negative 890 kilojoules for every 2 moles. And it's okay to do that way, you know, with the 2 on there. And there it is, 20 divided by 18.02. Gives you the moles. Times 890 divided by 2 is 494. Again, negative 494 kilojoules. Now, all right. So that's how you do the assignment. It's not very long, and I kind of want to jump to the calorimetry, and I probably will do that too, so we get a lot of things done here. But I will say this, that well, that's all I got to bring up there. That's all I'm going to say. I'll also let you try and do the homework. But there's a little something on the very last problem. I told you to do A through F. F has a little surprise there. See if you can figure it out. And then I say that you might be able to figure it out quick. All right, that is all for that one. I'll see you guys